This is Mr. Beck Does Your Homework. We're doing questions 8 and 9 together here. Question 8 says, a child of mass 46 kilograms sits on the edge of a merry-go-round with a radius 1.3 meters and moment of inertia of this many kilogram meters squared. The merry-go-round rotates with an angular velocity of 2.4 radians per second. What radial force does the child have to exert to stay on the merry-go-round? This question is only tricky because you have to remember how to deal with centripetal force. Because the child is sitting here somewhere on the outside of the merry-go-round. In order to stay without falling off, if there were no forces acting on the child, if all forces were balanced, the child would wind up going off in a straight line and sliding off the merry-go-round. So instead, the child needs a force that's directed towards the center in order to stay on the merry-go-round. It turns out that force is going to be a frictional force. But that's irrelevant here because that force is going to be m times v squared over r. So I'm given the radius, which is going to be my r. I'm given a velocity, but I'm given an angular velocity of 2.4 radians per second. So I'm going to have to convert that. And then my mass is 46 kilograms. So that's the mass. Now, I also know the relationship between v and omega. Since I'm given radians per second, I know that my velocity is going to be my omega times r. And if I'm smart, I can plug that into my equation already. So instead of mv squared over r, I'm going to get m times omega squared times r squared over r. And that's going to cancel out one of these r's. So now I don't have to worry about the velocity itself. So that'll give me my mass times my omega squared times r will give me the centripetal force necessary to move around in the circle. Now for question 9, the child then walks towards the center of the merry-go-round and stops at a distance this from the center. Now what is the angular velocity of the merry-go-round? So we have to assume this merry-go-round is frictionless and moving around on its own, but I have some angular momentum here that is going to equal the angular momentum later when he moves in towards the center. So the kid is actually going to be moving in towards the center, and you should have an instinct now that as he moves in towards the center, the merry-go-round should spin quicker. So what I have is L equals L. Each L is going to be my I omega beforehand, is going to be my I omega afterwards. The moment of inertia is going to be the total moment of inertia of the kid and the merry-go-round because they're spinning at the same rate. So I am going to have the moment of inertia for the merry-go-round is given in this number. And then the moment of inertia of the child is going to be, so I'm given that number, and to that I'm going to add the moment of inertia of the child, and since it's a point mass moving around a circle, he is going to be mr squared. So that is going to be my moment of inertia total. Initially, I have 1 omega, and that's going to equal my, it's going to be the same sorts of things. It's going to be the I again of the merry-go-round plus mr squared. Let me zoom in a little bit here and actually move it over. So it's going to be an mr squared times an omega over here. Now be careful because the r's are going to change. Initially, my r is 1.3 meters for me, and later on my r is only 0.546. So use your own numbers there, but you see you've got a radius here and you've got a radius here, how far he is from the center. So you're going to use this radius here, you can use this radius here, and the moment of inertia of the merry-go-round itself stays the same. So you have an initial omega that they're given in radians per second, and you've got a final omega. So you've got to solve for your final omega, and I think you can take it from here.